Okay, multiplying and simplifying radicals. So you want to recall from the multiplication property of square roots that yesterday you wrote down the square root of 54 could be broken down into the product of two radicals, the square root of 9 times the square root of 6, and that's actually the method that we use if you are chunking. You try and break it down into two square roots, one of which is a perfect square. So the thing with this is you can actually go back and forth. So if we can break one radical down into the product of two radicals, we can also turn around and take the product of two radicals and put those factors under the same radical. Okay, so what that means is if we have the square root of 8 times the square root of 12, so we're performing multiplication on those radicals, then rather than simplifying each of these separately and then worrying about the multiplication because it might simplify again, what we're going to do is put the factors of 8 and 12 under the same bar. Okay? You could multiply 8 times 12 and you get 96, right? But then you'd have to turn around and break down 96, and factors of 96 are already 8 and 12. So rather than multiply and then turn around and take them apart, we're going to take them apart and put them all together in the same bar and then worry about what comes out. Okay? So when we break down 8, we have 2 times 4 and 2 times 2. And when we break down 12, we have 2 times 6 and 2 times 3. So if 8 times 12 is 96, then all of these should be the factors of 96, right? So we're going to put these all in the same radical. So 1, 2, 3, 4, 5 2's and a 3. We're going to take out the pairs. So inside my radical is 6, and outside would be 4. So the answer to what is the radical 8 times the radical 12 would be 4 radical 6. Okay. So what I'm saying is you do not have to multiply 8 times 12 and get 96 and then turn around and do a tree for 96. It's a waste of time because you're going to break apart 96, right? So whatever you're multiplying that's in the radical, you might as well take those factors and put them in the same radical and then worry about what comes out. Okay, so the next one we're going to look at is slightly different. Well, let me have you do an example like that first. Okay, so this one looks just like the one we did. Now, what if you have something in the radical that's prime? Does that simplify? I mean, there's no point in doing 13 times 1 just to get a tree. It's prime. There really is no tree, and we don't need 1. Okay, 1 doesn't do anything. So, but 52 on the other hand, what goes into 52? 2 and 26. And 2 and 13, right? So don't forget, you do need this guy over here. Even though there's no factors under that tree, you need the 13. So what we're doing is under the same radical, we have the 2's, and we have the pair of 13's. We haven't spent a lot of time talking about it, but everything under the radical has a partner. What does that mean? It's all a perfect square, right? Everything's coming out. So if everything comes out, do you still need the radical? No. So the 2 comes out, and the 13 comes out, and we don't need the radical because there's nothing left in it. So our answer to this would be 2 times 13, or 26.
Do we put the square thing on the 26 or it's just...
No, because if we said, okay, here's the radical, what stays in it? Nothing.
Oh,
You know what I mean? So we don't want the radical. All right. So let's talk about what happens with something like that. Okay. So you already have 2 numbers that are outside of your radical. Is there ever any reason to put them back in? Do we want to add to the radical? Stuff that's already out? No. Our goal is to get out the perfect square. So if something's already out and we're going to put these together, this is multiplication. So what do you suppose happens to the 3 and the 4? They multiply and become 12. Okay? 2 and b aren't going to break down any further, so we're just going to pop those in. I'm putting b at the end to make it easier when I put the other stuff in. What about 10?
5 and 2.
That'd be 2 and 5, so we'll put the 2 and the 5 here, and then we've got that other b. So those are all my factors that are currently in the radicals. I have a pair of 2's and a pair of b's. So what should stay in? The 5 is in. The 2 comes out, but there's already a 12 out there, so what do I do with that? Yeah, I'm going to multiply the 2 by the 12, so that would be 24, and a b. And that's my simplified answer. Okay, so you guys are going to do one more example here. So try this one on your own. All right, let's deal with the 2 and the 6 first. What happens to those? They become 12 in front. And I've got a 5. That's not going to break down. And I've got 10. That is 5 times 2, right? So there's a 5 and a 2. And what about the A's? Take one A off of the 3, so there's an A, and then I have a pair of 2's and a pair of 2's, so I have A to the 4th. Altogether I have 5. Did I just confuse anyone there? I have 2 here and 3 there, so I have 5. I took 1 off and made the rest 4, because that 1 is going to stay in, right? So my pairs are here and here. The 5 comes out, and the 5 and the 12 become what? 12 times 5 is 60. And a to the fourth comes out as a squared, and still hanging out in the radical is 2a.
How would it become a squared?
Because you take half of those. Because if I were to list those out, I'd have 5 A's, right? 2 pairs and 1 oddball. So one of each pair comes out, which is what gives me the 2. But I can take that shortcut by doing half of my exponent on the outside. All right, one last example.